Take a look at these two rocks. You might not believe they were born from the exact same process. On one hand, we have this speckled granite, full of big, shiny crystals. And on the other, this piece of obsidian, a shard of pure, black glass. They look like they have nothing in common. But geologists call both of them igneous rocks, born from incredible fire. So why the dramatic difference? The answer is a secret code, written into the texture of every rock you've ever seen. It's a code that tells the story of its birth. And today, we're going to learn how to read it. These aren't just stones, they're frozen moments from Earth's violent and beautiful history. Once you understand their code, you'll never look at a rock the same way again. The key to the code, the entire secret to decoding these rocks, comes down to one surprisingly simple thing: how fast they cooled down. Every igneous rock started its life as magma, a superheated liquid mix of molten rock, minerals, and gases. But where that magma cools determines everything about the rock it becomes. Geologists have two names for molten rock, and that small difference is the key to this whole story. When it's trapped deep underground, it's called magma. But once it erupts onto the surface from a volcano, we call it lava. And the difference between cooling slowly in a chamber miles below ground versus cooling almost instantly in the open air is what makes a rock full of giant crystals or a rock made of pure glass. Think of it like this: imagine you have a pot of very salty water. If you let it evaporate slowly over a few weeks, you'll grow big, beautiful salt crystals. But if you splash that same water onto a hot skillet, it flashes into steam, leaving behind just a thin crust. The exact same principle applies to rocks. Slow cooling gives crystals time to grow. Fast cooling doesn't. This one difference splits all igneous rocks into two big families. The first are intrusive rocks, which form when magma gets trapped, or intrudes, into the crust and cools down there. The second are extrusive rocks, which form when lava exits the earth and cools on the surface. The slow and steady world below. Let's start our journey miles beneath our feet. Down here, in vast, insulated chambers, giant blobs of magma slowly start to lose their heat. And this isn't a quick process. The cooling can take thousands, or even millions, of years. This is the home of intrusive igneous rocks. A perfect example is this piece of granite. Look closely. It's not one solid color, is it? It's a mosaic of interlocking crystals, pink, white, and black. Each of those visible specks is a different mineral. Because the magma cooled so incredibly slowly, each mineral had plenty of time to organize itself, growing atom by atom into a large, defined crystal before locking into place with its neighbors. The coarse, grainy texture you can see with your own eyes is the dead giveaway of a rock that had a long and slow birth deep underground. When you look at a granite countertop, you're literally looking at the inside of an ancient magma chamber, a place that was once the glowing, liquid heart of a mountain range. The size of those crystals is like a time stamp, telling a story of patience over a geological timescale that's almost impossible to wrap your head around. Every single crystal is a clue, a record of a slow journey from liquid to solid, hidden for eons until time and erosion finally brought it up to the surface. The fast and furious world above now. Let's leave that calm, slow cooling world behind and head to the surface for the other half of the story. What happens when that same magma doesn't stay trapped, but finds a way out and erupts as lava? This is the world of extrusive rocks, and its story is all about speed and chaos. When lava, which can be over 1,000 degrees Celsius, hits the cold air or water, it cools in a geological instant. There's just no time for large crystals to grow. The result is a rock with a totally different feel. A great example is basalt, one of the most common rocks on our planet. It's dark and dense, and if you look closely, you can't see any individual crystals. They're in there, but they're microscopic, frozen in place the moment the lava hardened. This fine-grained texture is the telltale sign of a rock that cooled quickly on the surface. But what if the cooling is even faster? What if it's practically instantaneous? Well, then you get this: obsidian. Obsidian is natural volcanic glass. It forms when lava cools so quickly, we're talking seconds or minutes, that there's no time for any crystals to form at all. The atoms are just frozen in a chaotic jumble, exactly like in window glass. Holding a piece of obsidian is like holding a lightning-fast moment of geologic time in your hand. And the story can get even wilder. If the erupting lava is full of trapped gases, like CO2 and water vapor, it can froth up just like a can of soda you've shaken. If that frothy lava cools fast, the bubbles get trapped inside, creating a texture called vesicular. Pumice is the classic example. It's so full of holes from those escaping gases that it's incredibly light, some pieces can even float. Every one of those tiny holes is the ghost of a gas bubble, a permanent souvenir from a violent, explosive eruption. So from the dense basalt of the ocean floor to the glassy shine of obsidian and the airy lightness of pumice, all extrusive rocks tell a story of a fast and furious birth on Earth's surface. If you're enjoying cracking this geological code, why not hit that subscribe button? Understanding these rocks doesn't just tell us about the past, it shows us that our planet is still incredibly active, with more secrets hiding in plain sight. Cracking the code and its deeper meaning. Alright, let's bring our rocks back together. On one side, we have granite, with its big, visible crystals telling us it cooled slowly, deep inside the earth. On the other side, we have basalt, obsidian, and pumice, whose fine-grained, glassy, or holy textures tell a story of a rapid, dramatic birth on the surface. This is the secret code. The number one rule for reading igneous rocks is, texture tells you the cooling story. Big crystals mean slow cooling. Tiny or no crystals mean fast cooling. But that's just the first part of the code. The other key factor is composition, the specific mix of minerals that make up the rock. This is what gives a rock its color and many of its properties. For example, granite and its extrusive twin, rhyolite, have a similar light-colored, silica-rich composition. The only difference is one cooled slowly and the other cooled quickly. The same goes for dark, iron-rich gabbro and basalt. One is intrusive, the other is extrusive. This combination of cooling history and chemical recipe is why we have over 700 different types of igneous rocks. Each one is a unique snapshot of the exact temperature, pressure, and chemistry that existed when and where it formed. And these rocks aren't just curiosities, they are the foundation of our world. Intrusive rocks like granite form the stable core of our continents. We use it for buildings and countertops because that interlocking crystal structure makes it incredibly strong. Extrusive rocks like basalt make up most of the ocean floor and build enormous volcanoes. We crush it up to make our roads. More importantly, these rocks are proof that our planet is alive. The rock cycle that formed them is still going. Volcanoes are erupting right now, making new extrusive rocks. And deep beneath our feet, magma is still moving, cooling, and creating intrusive rocks that might one day be pushed to the surface. These rocks are a constant reminder that the Earth isn't some static ball of rock, but a dynamic engine, constantly reshaping itself from the inside out. So, the next time you pick up a rock on a trail, or just notice a stone building, take a second. Don't just see a rock. Look for the code. Are there large, glittering crystals locked together? You're looking at the heart of an ancient magma chamber that took thousands of years to cool. Is it dark and fine-grained? You might be holding a piece of a lava flow. Is it glassy or full of holes? You're seeing the split-second aftermath of a volcanic eruption. Every rock tells a story. They're archives of deep time, with tales of fiery explosions and of slow, patient work happening deep inside the earth. And you don't need to be a geologist to read them. Now, you have the key to the code. You have the secret to unlocking the ancient, dramatic history hidden all around us. What's the most interesting rock story you learned today? Let me know down in the comments. And if you had fun cracking this code with us and want to unravel more of our planet's mysteries, be sure to hit like, subscribe, and join us for the next one.